Well, good morning, everybody. Thanks for joining us in this cozy venue today. I also want to thank my team and the SPE for all the support in putting this stuff together. I've had a heck of a time doing this. It's been a lot of fun. I hope the Anderson Thompson team has as well. We put a lot of effort and time into doing this, and we've had a blast doing it. And I think hopefully we've created some good video content as a result. So this morning, well, let's actually cue this up as a slideshow. There we go. There's always that brief pause where you're wondering if technology is going to fail you or not. So on with my talk. The Edge of Tomorrow: How Completion Technology will drive the oil and gas industry forward. So before we begin, we always have this sort of ritual where we introduce the team, Anderson Thompson. I'll spend just 30 seconds or so. You guys have heard the spiel already. But you know, I do like to tout our abilities, and I'll spend a bit of time talking about what we do. So Anderson Thompson is basically we're reservoir engineering consultants. We provide an integrated approach, and I almost call it like we act a little bit as a shadow asset team. So we work with oil and gas companies, large and small. We work with private equity. We work with investors, and our goal is basically very simple. It's to use all the information that we have available to us to help optimize field development, and that could be something as small as just designing a completion to as large as looking at some undrilled acreage and finding out what's the best way to exploit it going forward. So we do a variety of different things, but we focus on a practical approach, and we also focus on an integrated approach. So we integrate the sciences of G&G, reservoir engineering, completion engineering, frac modeling all together. So today I'm going to talk about completion technology. This is obviously something that's very important in the industry. And I want to sort of take this in three parts in order to really understand how we got to where we are and where we're going to go in the future. We have to look at the past. So I'm going to review some statistics and trends on the drilling and completion and production side that I'm sure that most of you are already more than familiar with, but I'm going to maybe add a little bit of color in my thoughts to how we got to where we are. And then let's talk about the present. Where are we at this point in time? Where do we go now? And I'm going to talk about something that my team has really sort of crystallized on this idea of fit-for-purpose well and completion design. So I'm going to give you my thoughts on what that means, and I'm excited about it. I think it's something that we can really embrace as an industry, and it will take us forward. And then we're going to move into the future. That's sort of the theme of this. And to help me talk about the future, I've brought along my colleague Eric Schmelzel. Nobody better in the industry to talk about cutting-edge completion technology trends than Eric. So he's going to help me out when we get to the third part and talk about some of the cutting-edge oil field technologies that are out there. So I don't know if you guys have seen the movie Edge of Tomorrow, but it's actually a really cool movie. One of the things, or the main theme of the movie, is this fella played by Tom Cruise, and he relives the same day over and over again. And every time, and it's a little bit bleak because he dies, and then he wakes up and relives the same day. And he's in a war, and he's battling aliens. And it's sort of like a puzzle, right? He gets a little bit further every time, and then he dies and has to figure it out and go through. So it's a little bit like a cycle. And the oil industry is obviously cyclical, so there's some parallels there. I'm going to start with price. This is always something that everybody's interested in. And the theme here is, we've been here before. So you're looking at gas price, and you're looking at oil price. So we started with the shale gas boom, which came as a result of a pent-up demand or supply gap, whatever you want to call it, that the industry eventually fueled and fed by this huge explosion in horizontal drilling technology, and the shale gas boom was born. And then, of course, we had the shale oil boom. And you could argue that we worked ourselves into low prices by doing that. of course, the industry was highly successful at creating a huge amount of hydrocarbons, oil and gas. But did we convert oil into money or money into oil? You know, which one are we trying to do here? So there are these cycles. You know, we have to live with them in oil and gas. We don't have a choice. But it's an interesting theme that we sort of keep doing the same thing over and over again. Let's look at the production. And I'm going to focus on U.S. Domestic production. You guys have all seen this chart. But when I look at it, I'm always astounded that the U.S. was able to double domestic production from 5 to 10 million barrels a day in just a few years, right? In just a period of about 5 years. So the shale oil boom in the U.S. was actually quite amazing. You know, and it doesn't. What you got to think about when you're looking at this is not just the additional production that you're creating. You're also covering the declining conventional production. You know, the peak production in the U.S. was something like in the early 1980s, and it's been declining ever since. And so the shale boom not only filled that decline gap, but also increased production. So it's actually quite an accomplishment. I want to spend a little bit of time talking about drilling and completion trends over the last 10 years. This information comes from IHS. And so overall, when we talk about just drilling, probably the single most important trend that led to this increased production that in the U.S. and Canada that we've enjoyed is drilling efficiency. Just the ability, and that's the green line on this plot. So just the ability to put more horizontal feet, meters, whatever you want to call it, of pipe in the ground faster per day. That's more than doubled in the last 10 years. In terms of well construction itself, lateral lengths have increased from 2,500 feet to 7,000 feet. You guys are going to notice that I'm going to switch between talking feet and meters and PSI and KPA. As a Canadian, of course, we have to do that when we're talking the lower 48. All the statistics come in imperial. When we're in Canada, everything's coming in metric. So average lateral lengths, dramatic increase. Average stage counts have increased from 5 to 25. Proppant loads, this is where it's really quite frightening in a way. The sheer amount of treatment intensity over the past 10 years has gone, if you're talking total proppant loads from 200,000 to about 7 million pounds. We're routinely doing 10 million plus pounds of treatment on wells these days. And so if you look at it from a treatment intensity perspective, we've gone from about 80 pounds per foot to 1,000 pounds per foot, which is quite an accomplishment, just purely in the logistics of making that happen. The real question is with all this stuff is how does that translate into performance? How does that, and we're going to look at that. When we look at north of the border here in Canada, these statistics are confined to the Montney, but that's where a lot of our focus and activity is here in Western Canada. So if we look at completed well length, and this is where I switch over to meters, in feet, those statistics are very similar to the US. So 2,100 meters is about 7,000 feet or something like that. And so it's trending up. Frac stages, same thing, average of 10 in 2010 to about 25 now. And proppant placed 750 tons to 2,500 tons in terms of total proppant load. That's the global oil market collapse in 2014. The interesting thing is you don't really see any sign of this industry in terms of our ability to make big wells and our willingness to make big wells slowing down at all. Okay? It's just sort of continuing to grow, which is a good thing. So how far will these trends continue to go? That's a question that we get asked quite a lot on my team and also the NCS guys, is how big are these completions going to get? How big should they get? When does it stop becoming economic to stretch that horizontal well out further or put that extra ton of proppant in the ground? I can tell you certainly from the perspective of what we're capable of doing, we haven't even come close to reaching that limit yet in terms of the averages. Eclipse drilled their Purple Haze well, I think earlier this year or last year, I can't remember, but it was 18,000 feet plus. Okay? So that's, in terms of capability, we can make these enormous wells, right? That's nowhere near what the average is right now. That's quite a bit further. In terms of sheer treatment size and intensity, Devon just drilled a well where they pumped 54 million pounds of frac sand in a horizontal well at an intensity of 5,000 pounds per lateral. So in terms of sheer well construction and treatment intensity, we're flexing our muscles there, right, as an industry. We can make this happen already. But you know, are we optimizing or perhaps overcapitalizing is one thing we might want to ask ourselves. So this, you know, these wells, I think, have a purpose in showing us as an industry what we're capable of doing, and they'll undoubtedly teach us some things, but it doesn't necessarily mean we should be drilling all our wells that way. Let's take a look specifically at the Montney. I'm going to do a little bit of a close-up look. And my good friend Lucas Ford at Verdazo helped me prepare some of these plots, and so thank you, Lucas, for that. We spent probably a couple hours on the phone looking at the details of this and trying to figure out what it all means. But I like these plots because it's sort of a simple way to look at statistics, right? And please take it, I'm going to say this a couple times in the presentation, take it with a grain of salt. If you guys saw the first presentation I gave, I talked a lot about the fallacy of data statistics. So just be careful. This is a blunt instrument. These are just averages that we're looking at. So this is all the Montney. But the nice thing about it is there's 1849 wells in here. Okay, so there's almost 2,000 wells. We can really get a sense of the average trends. And so what I want to do is I want to look at 3 different statistics that I think are very important. One of them is well length. One is stage count, and one is proppant intensity or treatment intensity. So we're going to look at well length first, I think. Yeah, we're going to look at well length first of all. And what we're plotting here, these are cum distributions, and what we're plotting here is 6-month gas produced per 100 meters well length. And if you guys recall in my first presentation, you know, it's a metric of just gas cum produced is not necessarily the best metric to say how a well is going to ultimately perform, but it's a pretty good metric, and it's the best we've got in terms of public data. So let's use that. And I wanted to use 6 months because, as opposed to 12 months, because I wanted to include wells that are recently drilled. So we wanted to, you know, use as recent data as we possibly could. So what you're looking at here is these various different binnings that you're seeing here are different horizontal well lengths. And we're reporting the 6-month cum per 100 meters of length. So what this shows us is there's somewhat of a tipping point or peak performance at around 1,500. That's the curve shown in yellow. And when the horizontal wells get longer than that, those curves start to move back on themselves in terms of gas produced per 100 meters of well length. So I hope that's clear. What that's really showing you, at least in terms of the averages, is that there is a place where you start to become less efficient. And that would be fully expected, right? As we're drilling these wells out longer, you're not going to get a fully scalable result. You're going to start to lose efficiencies. I want to look at the same information now in terms of cost, because in Canada we get a pretty good cost database available to us that we can add in there as well. But again, just, you know, the caveat here is we're dealing with public data. It's not perfect data source, but at least gives us an idea of the trends. If we look at it in terms of cost, we can actually push that envelope further. So that's telling us that we can get to about 2,500 meters, even though we're losing efficiencies purely in terms of per meter gas produced. In terms of cost, we can actually start drilling those out further, and on the average anyways, we're still getting good cost effectiveness. So sorry, I got ahead of myself and didn't explain what we're plotting here. This is 6-month gas cum plotted per $1,000 of CapEx. Okay. So now that you get the idea of what we're doing there, let's look at the same type of plots now for the 2 other variables that we're interested in. One is stage spacing. Okay, that's what we're going to look at now, and then we'll do treatment intensity after that. So this is stage spacing. In this plot, the green curve, as you would expect, is the lowest stage spacing or the highest stage density, however you want to look at it. And the gray curve at the back is the largest or least dense stage spacing. So this is exactly what you would expect. You'd expect the average performance to go up as the spacing starts to decrease. So there's no surprises there. What about in terms of cost? So how cost effective is denser spacing? Well, as expected, these curves start to collapse in on each other, and what we actually see is right around 75 to 150. We really don't, as we get less than 75 meters, we don't see any improvement in cost effectiveness. So I see that a little bit as a limitation in our technology. We need to drive the technology to the point where we can start doing denser spacing at a lower cost, because we will get the performance out of the wells, at least on the average. Again, you have to look at this in terms of specific areas. This is all of the Montney, and we don't want to treat it with, paint it with all the same brush. But at least in terms of the averages, that's what it seems to show us. Let's look at how scalable well performance is to treatment size, so sheer proppant volume. As we would expect here, there's a trend as we move towards the right. The treatment intensity increases. So what we're plotting here is tons of proppant pumped per 100 meters of well length. So it's a treatment intensity figure or density figure. The interesting thing about this one, and this may just be unique to the area that we're looking at, is for some reason when we get into the really high intensity treatments, 150 to 200 tons per 100 meters, and it's hard to see it on this plot, but there are 130 samples in that bin, and they're actually among the worst producers. And so that's a big question mark. Why did that happen, right? It seems to peak at 100 to 150 tons, and then we actually see, on average, a loss in productivity observed for treatments that are larger than that. So I sort of scratched my head a little bit on that one. Lucas and I talked a bit about that, and what we found, and it doesn't show up on here, but all of these gray wells were clustered in one particular spot. So that's a geology thing, I think, more than anything. It's probably an area of the Montney where they weren't getting the performance maybe that they wanted, so they were trying larger treatment sizes and maybe not getting the result that we're seeing in some of the more successful areas. So in general, I think it tells us the story that we would expect to see. In terms of cost effectiveness for treatment intensity, what we see here is it maxes out basically at about 50 to 100 tons per 100 meters, and that's where we're getting approximately 170 MCF per $1,000 of CapEx spent. So cost effectiveness of horizontal completions appears to diminish beyond 100 tons. Again, there may be some false data in there or some hidden variables simply because we're mixing geologies, right? We're not doing this on a consistent geological basis, and there may be a grouping of wells in here that just don't perform as well. In any case, that settles out to about 670 or close to 700 pounds per foot in terms of treatment intensity. So again, conclusions served with caveats. Take this with a grain of, not because Montney's a siltstone, grain of silt. We're looking at large geologically diverse data sets. We're using an imperfect metric, 6-month GP, to measure performance, and we're relying on imperfect data. If you can sort of sit with those assumptions, we can actually pull some decent conclusions out of this, at least on the average, and we have to treat it as an average. Cost effectiveness of wellbore length starts to diminish beyond about 2,500 meters or 8,200 feet. So I didn't have a good answer to this question before. Now going through the exercise of looking at this data, I have a pretty good answer, at least in the Montney, in terms of averages where we start to have that tipping point. There's room to increase stage density in the Montney, but cost efficiencies need to improve. I think this is an area where completion technology can really help us. Cost effectiveness of treatment intensity starts to diminish at about the 1 ton per meter mark, which is about 700 pounds per foot. That's the Montney. Devon did their 5,000 pounds per foot well in the stack. So there's a huge gap there, right? So does that mean we shouldn't be increasing treatment intensity beyond that? No, it doesn't mean that. It just means on the average. There is some decent perm stuff in the Montney that's mixed up with the low perm stuff, and we're sort of lumping it all together. So that's the Montney. What about the lower 48? So let's talk a little bit about the U.S. And we need to talk about the U.S. Because really that's where the bulk of the shale oil revolution has occurred. In fact, if you take the Permian, Eagle Ford, and Bakken, and if you were to sort of pretend that that was a self-governing country out on its own, it would be, with those 3 plays alone, it would be the 5th largest oil producer in the world. after China. So that's quite astounding when you look at the statistics on that. So these 3 plays by themselves are responsible for the vast majority of the doubling of US domestic production supply over the last 10 years. What I'm really interested in, so it's obvious that the production is there, okay, but how did we get that production? Did that simply come from just drilling more wells, or did it come from drilling better wells in addition? So the EIA has done some good work in sort of compiling some of these statistics. And what we see, and I like these plots because they show year-over-year well profiles, average well profiles. And of course, we've got to be careful when we're doing averaging with type wells. I understand that. But again, it's just a rough sort of metric to really get a sense for what's going on. And there's a couple things we can see from these plots. One is that every single one of those plays, all 3 of them show year-on-year growth in average production performance. Every one of them do. But they're not all created equal. For example, in the Eagle Ford and Bakken, what you see if you look carefully is that you're starting to see diminishing returns. The improvement is there, but it's getting less and less per year. And eventually what you're going to see, and it's happening already in plays like the Eagle Ford, is these curves will start crossing each other. The reason is the Eagle Ford and Bakken are somewhat mature plays, and wells that are being drilled now are infill locations in many cases. And so you're starting to see a dropping in performance. And certainly you can see it in the overall production in those plays. They're starting to decline already. What's happening in the Permian is a little bit different. The Permian is still displaying growth that looks scalable, right? It looks like it's still in full sort of development mode. And that seems to be the case. And that's why the Permian is a hot area right now. There's many different plays and subbasins in there. And a lot of exploration, a lot of areas where the land hasn't even been locked up yet, and companies are still really going gangbusters and drilling in there. So that's really what the landscape looks like in the US. Of course, there are many other plays that I'm not covering here. These are the ones that, just from the pure numbers and statistics, these are the ones that are of the most interest. But of course, there's many other ones that we can look at. What about costs in the US? This comes from IHS. If we look at all the different plays, again, what I'm more interested in here is the overall trend. I was surprised when I saw this chart because what it really shows is that D&C costs, at least in the lower 48, have been declining since 2012. So even long before the collapse of the global oil market, we started seeing these costs coming down. And in fact, we're at a cost efficiency point right now that's the same as where we were 10 years ago. So that's great, right? We've brought the costs down. It's good news. Let's continue the sort of talk about economics. And this is specific to Texas, but I really like this plot. One of the reasons I like this is because it teaches you that this whole averaging thing that I'm doing can be dangerous. Okay? What you're seeing here, these bars are all broken down. Every one of those bars represents a county in Texas. And the color coding represents different shale plays that we know. For example, the pink one is Wolfcamp. So let's look at Wolfcamp. And what we're measuring here is break-even per BOE. So in the Wolfcamp, we range all the way from $23 break-even all the way to the maximum, which is $59. So even when you're within a play, counties that are comprising that play can have vastly different economics. And that's because you've got different operators working in there, you've got different geology. There's a huge amount of texture when we get into the real nitty-gritty of the details. And so the break-even prices are all over the map, okay? And ranging everywhere from the low 20s all the way up to 60 and higher. Let's expand the view. So that was sort of a down-in-the-weeds view. Let's expand the view and look more in terms of the whole North American picture. And so these are break-evens for plays across the board, and we've got Canada and the US in there. And a couple things I want to show. One is that Canadian plays are competitive. That's great news. The dark dots that you're seeing in here are break-even prices for Canadian plays. Bad news is they're not necessarily economic across the board, right? This is as of November 22nd. We were at $50 US WTI. And some of these assets are doing well, but there's a huge majority of them, especially in the lower 48, that are they're not economic at these prices, right? So we, as an industry, and we'll get to that theme later on, we need to obviously do something about that. Okay, so I've spouted a lot of statistics. I've talked about, you know, increases, production increases. I've talked a little bit about some trends that I think are driving performance from a very broad basis. What made all this possible? And I think I spent some time talking to some of the folks that are back at our office and some operators as well, to get everybody's opinion on this and try to get a good sense of you know, what have been the technological game changers that have taken us to where we are now. Because if we can understand that, then maybe we can understand what's going to drive us in the future. And what I'm going to say here, you know, agree with it if you like or not, is that the game changers up until now have been decidedly low-tech, okay? Really simple things, but really powerful things. For example, pad drilling. There are some high-tech elements of that, obviously, but pad drilling is probably the single most important economy of scale tool that we've harnessed as an industry that's allowed us to get to where we are now in terms of the vast amount of production increase that we've enjoyed. Scalable, efficient placement of pipe in the ground, it lowers capital cost per foot or per meter of well drilled. Multi-stage completions is the second one. Without multi-stage completions, we wouldn't have any of this, because we simply wouldn't have been able to make any of these wells produce the way we have and make them economic. So multi-stage completions has allowed us to execute compartmentalized stimulation. And I'm going to carry on with that theme. You're going to see that later on. We'll talk about being able to compartmentalize a stimulation. And that, of course, lowers cost and increases production. So we get a double value there. And then, of course, slick water fracturing. Again, decidedly low-tech in many ways. You know, we went as an industry to spending billions of dollars on things like gel breakers and additives to frac fluid, and now we're back at the point where we're just using slick water. In fact, I heard yesterday that there's operators in some places that aren't even putting friction reducers in their frac fluid anymore. They're just going back to, you know, produced effluent and pumping that as frac fluid. So what does that really mean? Does it mean we don't need all these technologies? No, it just means a lot of times the simplest answer is the best answer. And slick water fracturing seems to have really taken on as a tool to, as a vehicle to produce these massive hydraulic fracture stimulations that that have made these big wells. So those are really the three technologies that I think have been critical in getting us to where we are. So that's where we are now. So where do we go from here? Okay. So if I could characterize the last 10 years, I would say it's been characterized by bigger is better. We use the big hammer, and that's great. That's gotten us a huge increase in production, and that's what was needed. Okay, that was driven by an enormous amount of pent-up demand that was in the U.S. If you think about it, the U.S. domestic supply had declined for a period of more than 20 or 30 years from its peak, and it's not easy to fill a supply gap that's that big. And as an industry, our industry did it with this giant hammer. So obviously the economic conditions are such that we can't continue to keep, it doesn't make sense to do that anymore, right? So we're sort of at a crossroads now. What are we going to do differently? Well, we're in a position now, of course, the economics are different, the landscape is different. We have the tools, we've developed the tools. Let's, instead of using the big hammer all the time, let's do fit for purpose. Let's use the right tool for the job that we're trying to solve. And I'm going to talk a little bit about that. And I'm going to say that what we're going to do in the next 10 years is going to be driven by the need for an abundant, low-cost, low-impact energy source, right? So rather than trying to fill a supply gap, which doesn't really seem to exist anymore, but there will always be a demand for oil and gas. We're going to need that resource in the future, but let's look at it as a fit-for-purpose type environment. So what do I mean by fit-for-purpose completions? I'm going to think of it a little bit as I want to coax the best that I can out of the reservoir. I want to bring the best out of that reservoir. There are several considerations that are important here, and I'm not going to touch on everything that's important, but I'm going to talk about what I think, at least in low permeability reservoirs, are some of the critical takeaways, some of the critical considerations as a reservoir engineer, a completion engineer, you have to think of when you're designing a completion. So obviously, total frac surface area, probably the most important thing, right? How much frac surface area do I need? How does that relate to treatment size? Another one is frac complexity, right? You hear a lot of people in the industry talking about frac complexity. In fact, I think frac complexity is somewhat of a controversial topic. There's people out there that are in the camp of, I can create fracture complexity with the frac treatment I'm doing. There's folks out there that say you can't influence that at all, and it's entirely Mother Nature. There's people out there that say there is no such thing as frac complexity. So we're going to talk a little bit about that. Maybe I'll say some things that are controversial. Hopefully it'll be interesting anyways. Frac conductivity. This is another one where there's a lot of controversy, right? There's a lot of discussion back and forth. Is how important is frac conductivity? I'm going to give you my thoughts on that. Okay, but these are important considerations because these are high dollar things you're spending your money on. Completion compartmentalization, easy for me to say, which really relates to frac stage density. Okay, so how many stages do I need? That's obviously another huge consideration. Well placement. This is one that's critically important in certain cases, and we'll talk a little bit about that. Where do I land that well, right? And what sort of trajectory do I use? And then completion technology. This deserves a lot more detail than I'm going to give it today, but I'm just going to give you a couple of simple examples. But completion technology is important, and a lot of times as an industry, we don't necessarily, we look at cost as being the main driving factor, but it's much more than that, right? You have to look at not only the cost, but how the benefit on the other end of it, how it's going to affect production, and look at it more as a net present value type thing. So the name of the game here is maximize effectiveness and reliability, minimize waste. You can think of well performance as a chain, okay? You don't get performance out of a well unless all of these elements come together. There's always going to be a weak link in that chain somewhere, and usually that weak link, or I'm going to say always that weak link, is what's going to drive performance. Whatever that weak link is, that's the thing that if you change it a little bit, it's going to either kill your well or make it way better. If you put a lot of effort into a link that's already strong, you can do it, and you'll still get a good well, but you're kind of wasteful by doing that. Okay? This is the best analogy I can think of, and I'll give you a couple different examples. One is designing high connectivity fracs in liquids-rich plays. And I already know by saying that that's a very controversial statement, and I'm gonna talk more about that, so you'll see why I have that opinion that that's the case. This one I think most people would agree with, using high frac stage density in what we would call, micromillidarcy, higher permeability. What you're really doing there is you're bolstering one of those links that's already strong. So it's not necessarily a bad thing. It's not going to negatively impact the well, but it's going to negatively impact your economics potentially. Okay, so the trick is really identifying what is that production driver and designing your completion around that. That's really what I mean by fit for purpose completion. So I want to show you some examples. Let's talk about frac surface area first of all. And you'll never know it's not permeability. We joked about this because from a reservoir engineering perspective, really our job is to look at what comes out of the wellhead. So how do I really know there's a frac down there? These equations tell me I don't necessarily know, because once I have a stabilized production rate, I can make this look exactly like this, or vice versa. I can make this look exactly like this. These are obviously very different well geometries, different permeabilities, but in terms of their stabilized production rate, I can make them exactly equal. And you would never know which one was which. And so we've always had this issue, right? When we, as reservoir engineers, we analyze production data, we don't know how much of it is because of frac area and how much is because of permeability. We have to use other metrics to understand that. But we can use these equations in our favor, basically as a way of calculating how much frac area we need. And this is sort of basic tool in the toolkit of the reservoir engineer. But a lot of times I find that these very simple calculations are not used in completion design. And they really should be. They should be used more. You can calculate how much frac area you need to achieve the production rates that you want to achieve. Okay? We can do that. And it's not always going to be the same frac area, surprise, surprise. If you have a higher permeability reservoir, you don't need as much frac area. So one way to think about this, in this specific example, I've got, let's say I've got a 1 millidarcy conventional reservoir, and I want to be able to reproduce the same stabilized production rate out of a reservoir that's got 1,000 times lower permeability. How am I going to do that? Well, this equation tells me how I can do that. In order to, for every foot into the reservoir I want to drain, I'm going to need 100 feet of frac length, or frac half length, to obtain that same production from that 1 millidarcy well. And you can use that at scalable to any permeability you want, right? So that equation works great. We use that one all the time. It's nice, we've got software and more advanced modeling. We can run the models that do this in a lot more detail and take into account the time and the transients and all that sort of stuff. But you should always do this because this is a gut check, right? And the software can just support that for the most part. So if we want to drain a quarter section in this example, we would actually need 13,000 and change feet of frac length. And that's, that would be impossible to achieve. So I guess what I'm saying is that if you have that reservoir rock that's 0.001 millidarcies, and we're exploiting rock that's a lot lower permeability than that. But if you want to be able to produce commercial production rates out of that, you're going to need 13,000 feet of frac length. And we can't accomplish that with one single vertical fracture. So this is where completion compartmentalization comes into play. Okay? I want to be able to deliver that 13,000 feet in staged completions, or staged delivery of that stimulation. And that allows me to efficiently create that 13,000 feet and get a great well out of it, get some sort of reasonable recovery rate of that resource. To illustrate the point, and this is real data, this is a log-log plot of and one is a vertical. You don't see too many vertical single-stage fractured wells anymore, but they are still kicking around. Most of them have been on production for many, many, many years. So there's a lot. There are a few of these around. This particular one has been on production for 200 months, and this straight line with a B value of 2 tells you that it hasn't seen any boundaries. So stimulated well, on the other hand, saw the boundaries after 18 days of production. And has multiples of better production rate out of basically the same rock. So compartmentalized completions have allowed us to do a couple things. One is create economic wells out of really crappy rock, and the other one is dramatically accelerate resource recovery in tight reservoirs, much more than we'd be able to do with just simple single-stage fracturing. Now we're at the point where we can actually optimize this. Okay, so that's the sort of the simple concept. Taking this to its extreme, we can look at cases and run these scenarios. Now we're getting beyond just back-of-the-napkin calculations. We have to run these through reservoir simulators and economics. But basically, what you end up with is a discounted cash flow forecast. This is net present value shown on the right-hand side. And what I'm doing here is comparing the economics of running various different stage spacings from 15 meters all the way to 150 meters. That's your break-even right there. Obviously, if you're going to do 15 meters, you've got a very, very high treatment intensity, and you're going to start with a lot of sunk D&C cost here, and obviously the economics in that case don't support it. It shows it very clearly there. So if we really wanted the optimized completion in this case, we could choose, really the yellow and the green are overlaying each other, so we could choose anywhere from, say, 60 to 75 meters, and you'd probably choose 75 meters because you spend a little bit less money on the front end. And that gives you your best net present value. Okay? So we need to have all the information to plug in there. It's equal parts Darcy's law and depletion and reservoir engineering along with economics. And we put those two things together and we can solve that problem quite nicely. All right, what about frac conductivity? This is where things are going to probably get a little controversial and happy to engage in conversation on this, because I know even within our team we've had lots of arguments about this. But if I could distill it down to just a couple of very, very key points that I think are important, and if nothing else, we won't get into the details of the equations and everything, but what I want to make a couple of points. One of them is that, yes, of course, you always have to have frac conductivity. Okay? If your frac doesn't have conductivity, it's not going to flow. What's important really is that frac conductivity, you can think of it a little bit as being graded on the curve. Okay? I remember when I went to university, a lot of our courses were graded on the curve. So if the performance in the class was on average very poor, you didn't really need to have to get a good mark, that good of a mark on the test to get an A. All you had to do was be the best in your class. The best in your class might have been 50% or 60%, right? I actually had a class like that, where 60% was like one of 2 actual passing grades, and that person got an A. It wasn't me. I failed. I was lower down in the pack. I failed the test, but I still passed the course. That's how hard it was. So I think of that. To me, that was a good analogy of what frac conductivity is like. Okay, and so let's think about reservoirs. There's 2 things in reservoirs that are important when we talk about conductivity. One of them is the viscosity of the fluid, and the other one is the permeability or flow capacity of the rock. And we put those 2 things together, one over top of the other, K over mu, and we call that mobility. Okay? So it depends on the rock itself, and it also depends on the fluid, not the fluid you produce at the wellhead, but the fluid that's flowing in the pore space. Those are the only 2 things that matter. And so if you have, I'm going to take 2 extremes. If you have a very low permeability rock and something like oil sitting inside it, which has very low mobility, oil has 50 to 100 times lower mobility than gas. So when you take those 2 things and combine them together, that becomes the weak link in your chain. The matrix fluid mobility is very poor. So the matrix and the fluid is struggling to deliver anything to that frac. That's the analogy of that is like my class that I took. I don't need to get that good of a mark to pass that course, right? My high strength proppants or designing for a huge amount of conductivity in that frac, you're overcapitalizing. You just don't need it. You need some conductivity, but you don't need that much. And I'm purposely talking in qualitatives here. I'm not giving numbers because I don't want to get into that, but certainly from a qualitative sense, this is true. On the other hand, if you're talking about a higher perm reservoir with gas, the opposite is going to be true. Now your frac actually becomes the weak link. Your frac becomes a choke point. So you can actually have a situation, and compounded with gas, because you can get things like non-Darcy flow. Not talking about you, Darcy. I'm talking about different Darcy, but that's a terrible joke. Sorry. Non-Darcy flow can cause this choke point as well. So the ability of the formation and the fluid to deliver flow into the frac is really going to dominate what sort of conductivity you need. So those are my comments on conductivity. Now let's talk about frac complexity. A couple of points I want to make here. Frac complexity, I think, is, again, this is going to come down to oil and gas. I think frac complexity is going to be critical for ultra-tight oil, and this is why. If we take 2 examples, oil and gas, the top crude diagram here is supposed to show complexity. The bottom is supposed to show when you don't have any complexity. Here's my perspective. I have no idea whether the reservoir has frac complexity or not. All I can do is, my area of expertise is analyzing the production data, and I'm making inferences based on my analysis of that production data. And what I can tell you is that when I look at production data, it always appears that the oil reservoirs have, from the RTA that we do, they have this evidence of enhanced permeability and this evidence of we've made an inference that it's frac complexity. And we argued about it we argued about it actually quite a bit yesterday and in the days leading up to this talk. What does that really mean? Does that mean we're creating frac complexity in oil reservoirs? I think the answer is no. I think the frac complexity is either there or it's not. It's Mother Nature that puts it there. But what I will say is that if you saturate the pore space with oil in an ultra-tight rock, you're not going to get any sort of Darcy flow through the porous media. You're only going to get flow through the fractures. So in order to get any sort of commercial oil, economic oil rates, you have to have some sort of fracture complexity in that oil well. The same is not necessarily true for gas. Gas molecules are much smaller. Gas is much more mobile. Still, in a non-complex situation, you can still get gas production. So in a gas scenario, you can get a great well if you have fracture complexity. So fracture complexity is always going to be beneficial, but it's going to really be a distinguishing factor between a good well and a poor well if oil is the fluid. So frac complexity creates a multiplicity of total frac area. That's a great thing to have. Obviously, it's going to add a huge amount of productive capability to any reservoir. But frac complexity is a dominant performance driver in ultra-tight oil-saturated reservoirs. I think that's a really important statement, that maybe the industry doesn't quite, particularly from the completion side, doesn't quite grasp and understand. Certainly, we don't necessarily apply this to the way we design all of our oil completions. Frac complexity, it's not that it's not important for gas, it is, but it's less important. It's less of a driving mechanism. We can still get good gas wells with purely just planar fracs and no complexity. And the reason I'm saying these things is because I've analyzed hundreds of these wells using rate transient analysis, and this is what we see from the production analysis. Influence of treatment design on frac complexity, I believe, is minimal. Can we influence and create complexity? Maybe a little bit, but Mother Nature accounts for that much of it. If the rock is not naturally going to break in a complex manner, there's little that you can do from a stimulation perspective to make that any better. So how do we create complexity where it doesn't exist? Well, we do it artificially by compartmentalizing our completion, right? We put more stages in there. So if we can't have natural complexity, we need to double up on our stage spacing and artificially create that complexity by compartmentalizing and creating more fractures. Next thing I want to talk about is well placement. You guys have seen some of this already in previous talks, one that Adam presented, and I think John presented one as well. This is something that we believe is very important. This is not rocket science. It's very simple, but I think it's an undervalued variable when many operating companies are thinking about well placement. Okay, where do you land your well? A lot of operators will answer that question, well, I'm going to land my well in the place that has the best porosity. My target depth, if I look at a log, my target depth is going to be in that place where I think I have the best hydrocarbon pore volume, the best hydrocarbon porosity. And that's, of course, that makes sense, right? That shouldn't be a mistake. I mean, that should make a lot of sense. But if you look at this example, in a lot of cases, and this is just a frac model run in a low-perm reservoir with significant gross pay thickness, the landing depth on here is in the best porosity. But you can see a lot of the fracture progresses downward, and only about 100 feet of that fracture is effective. The rest of it is ineffective at the bottom because the viscous forces can't overcome the gravity forces, and you can't lift those liquids out of the bottom of that frac. Very, very simple, simple physics there. Make gravity your friend. So in the other frac model, we put the perf site 50 feet lower towards the bottom. You're going to be careful. If there is water down here, you don't want to put it too low. So designing where that landing target should be is not simple. Okay, we don't want to oversimplify it, but it's not necessarily going to be in the spot where the best porosity is. If you land it lower, then we can actually make much more of that frac height effective because you're making gravity work for you, not against you. Let's talk about one more thing, and that's the impact of completion technology. This is the subtlety that a lot of people don't see, but it's, the Anderson-Thompson team works with NCS obviously on a regular basis, and this is a big part of our research in the past is looking at, for example, how what sort of reservoir value can be provided by pinpoint completions. And I'm going to make this a little bit simpler and just say, let's look at the impact of cluster effectiveness. 98 or something % of all the wells, that might not be the right statistic, but it's above 90% of all the wells that are drilled, tight gas, tight oil wells drilled in the lower 48 in the United States are cemented liner plug-and perf wells. So perf cluster effectiveness is a huge deal, right? It's going to be, even if it's only like a 1 or 2% difference, it's going to be in 98 or whatever is 95% of the wells. It's going to be something that we have to consider. So if we only have, and the pervasive thought in the industry, and most people would agree, there's lots of literature to support this, is that we're really only getting about 50% effectiveness. in a plug-and-perf type completion with the technology that we have right now. If we simulate that, we get a picture that looks something like this. And it's not a bad thing. It just shows you basically that the red spots, all the sort of heat map, the red spots in here are areas that aren't being drained efficiently. Okay? And the green spots and the blue spots are areas that we're draining more efficiently. That's what 50% cluster effectiveness looks like. So multiply that by basically almost every single well that's drilled in the lower 48. Okay? This is the sort of picture that we're getting. In Canada, the landscape is a little bit different. There's a lot more open hole completions. And I don't really know how to simulate production response from open hole completions because we're not necessarily sure where the fracs are going. So it's a lot easier to compare 50% effectiveness in a cemented completion with 100% effectiveness in a cemented completion. And that's what it looks like when we run those models. This concept, this idea, we're putting into a paper that we're going to be presenting at CURC in February. So there'll be a lot more coming on this. But if we take this now and translate it into actual recovery profiles for the 50% and 100% case, there is a measurable difference. And in this particular example, I forget what the permeability was, but it was a tight reservoir. I think we took reservoir characteristics that would be indicative of something. What we see in the first 5 years is we already have an uplift of about 150,000 barrels from just going from 50 to 100%. And that equates to about $7.5 million at $50 oil. So it's significant. So let's review, and I'll go through these ones pretty quick. But the idea here is let's look at the full landscape of all these plays, and we're looking at a permeability scale here. And really, again, all I want to do here is, and I don't put any numbers on here, I'm not trying to get into the details, I just want to show in a relative sense what's important in low permeability completions and what's important in higher permeability completions. This is all what I would call conventional tight being the high perm scale and ultra tight being the low perm scale. So what's important in ultra tight, very low permeability, is frac area and stage spacing. What's important in conventional tight is frac conductivity and well spacing. I didn't really get into well spacing, but that's going to be a critical driver in higher perm plays because we start to reach the boundaries of volumetric boundaries of well spacing a lot quicker. So it becomes a much more important consideration. The other thing I want to look at is liquid content, because whether you're doing a completion for gas or whether you're doing a completion for oil is going to be a critical difference in how you want to design that. So for dry gas, frac area, frac conductivity are going to be more important. For black oil, well placement, that's what I talked about, making gravity your friend. That's going to be critically important. Fracture complexity, we already talked about that. That's going to be critically important for oil cases. One of the reasons I wanted to do these two plots and show specific examples of plays that are there is to really indicate that the areas that we're the most interested in oftentimes are in this middle area, which makes it more difficult, right? If we were on one end of the end members, then we know, there's going to be this one dominant thing that's really important. But a lot of times we're kind of in this gray area where we have to consider all of these things together. How much performance is coming from the reservoir rock itself? How much is really dominated by the fractures? Sometimes we're kind of in this middle zone, this no man's land, which makes it challenging, right? As an industry, building that fit-for-purpose completion can be very challenging. All right, so section 3, how will we get there? This is a shout out to all my US buddies. So how will we get there? Cutting edge technology, and in a minute I'm going to have Eric come up and continue the talk on cutting edge technologies. I'm going to say a couple more things before we get there. And I'm going to say that the most important thing, we bring back this break-even BOE or dollars per BOE. When we're talking about using technology and what we need to do in the future, this is all that matters. Okay. So today or yesterday or whatever, we had $50 WTI price. We want to drive those blue dots down. If we're going to continue to use these plays as our playground, I'm not saying anything that anybody would disagree with, right? We want to be able to drive the break-even price down. Any technology that becomes a game changer is going to have to do that. Otherwise, the only other thing we can do is find other, explore and find other plays, which we will do. But the significant component of technology will have to work in that direction for us. Just a couple more things. You may have heard of this idea of Shale 2.0. I'm going to say that probably the single biggest future technology, distinguishing technology, is going to be the use of information. This industry has collected terabytes and terabytes of data over the past few years, over just the past 5 or 6 years. And so a fellow named Mark Mills at the Manhattan Institute came up with this concept of Shale 2.0. It's kind of a cool concept, but it was devised by somebody who's not an oil and gas professional. So there's some stuff in there that's like, I sort of look at, and say, okay, well, we wouldn't do it that way. But there's some overriding concepts in here that I think are useful, right? And certainly one of them, as a stretch target, is to look at the ability to lower break-even costs. Can we bring them down to $5 to $20 per barrel? I don't know if we can get them that low, but certainly something to shoot for. How are we going to do that? Well, there's really two areas that are important that we can take a look at. One is data-driven models, so understanding the importance of multiple variables on well performance. This plot came from my good friend Samantha Foster at Canadian Discovery, and they do these data analytics, which I think are really powerful. They harness some technology that the oil industry hasn't really embraced fully yet, machine learning methods and genetic algorithms and things like that. But this is simply a sort of decision tree that allows you to cluster, and it does it sort of, there's an automated procedure for doing this, going through large volumes of data and figuring out and grouping and figuring out what's important, and then coming up with sort of, this was done for a particular area of the Montney, and the conclusion was that there's, on average, you're going to get a better well if you follow this sort of recipe. And it's not a deterministic thing, right? It's not like a guarantee, I follow this recipe, I get this result. But statistically, it's going to give you a better answer. One more comment to make here. Another area where information technology can be really, really valuable and is already extremely valuable is this idea of drill smarter, not harder. Okay? The idea here is we're going to find the sweet spots. If we look at the last 10 years, the big hammer is basically manufacturing operation, drill, 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 drill. This is taking it to the next level and it's saying, no, let's use all the data we have available, which includes a huge amount, terabytes of seismic data, integrating that with petrophysics, integrating that with frac models, integrating that with production, and creating a 3D production attribute map, an actual full 3D cube of the heat spots in here. That's where you want to drill to give you your best chance of getting a productive well or productive stage. So that's some pretty cool stuff. Laredo Petroleum is doing this. A lot of other companies are doing this sort of work as well. So final thoughts, and then I'll hand it over to Eric. I'm already running a bit over time. But unprecedented North American production growth over the last 10 years came from relatively simple technologies, but they were driven by economies of scale. The next 10 years will not and cannot look the same, obviously. We need to fine-tune our approach, focus on effectiveness, reliability, minimizing waste, use the enormous amount of information we've collected in recent years to make better decisions. New technology adoption will always play a major role in oil and gas development in the coming years. So I'm going to hand it over to Eric now, and he's going to talk about a few more exciting technologies. And we'll try and do a mic switch here. See how well that goes.
All right. Well, I'm going to go a little bit quick because, as you said, we're imposing on your time already. In sticking with the movie theme, he's the star, I'm the supporting actor. So I got tagged in at the end simply because we went through the presentation that David prepared, and it kind of led us to the edge of this. We got to do it different tomorrow. But what does that look like? And I looked at the title of this, and The Edge of Tomorrow, how completion technology will drive. That's not really what I can give you today. I can give you why, but I can't tell you how, because frankly, the next big thing, the next evolution in the oil and gas industry, completions, hasn't been deployed yet, hasn't been invented yet in many cases. But I'm going to just share 3 things that are out there in the ether now, just to help us open up our minds a little bit to, what the edge of tomorrow might look like. Of course, today, we're on the edge. Some of us have been on that edge since 2014. But I think everybody appreciates pulling harder on the oars might not be a viable alternative for us in the future. Dave went through how orders of magnitude scale has driven us to where we are today. In the future, we're going to have to change all that. And dollars per BOE is the metric. Those that successfully negotiate that one metric will survive, and those that do not will not. And that goes across the globe. It doesn't go just across the Canadian industry or the US industry. It's going to be those producers that can achieve that, because we are on the edge of a universe that is starting to accept the meme that this is not lower for longer. This is lower forever. And if your mind goes there, then you start to realize what a real race this is. Completions are fracs today. That might change one day, but for the time being, we haven't quite figured out how not to frac a well or how to replace fracturing in a well. And when it comes to fracs, we can only do one of 2 things. We either change what we use to frac the well, or we change how we frac the well. What are our methods? And so when we're chasing that cost per BOE produced, we've driven down completion costs by doing the evolution from gel to slick water to wastewater, as Dave touched on. Frac companies built entire differentiating technologies around frac gels, frac fluid systems, because horsepower is a commodity and you can't get a premium for commodities. So it all became an issue about, our gel is better than theirs, it breaks cleaner, it does different things. And the evolution of slick water kind of wiped all of that technology, all of that development, hundreds of millions of dollars in research and R&D off the table. Frankly, it doesn't even apply anymore in 90+% of the wells. And so all of the chemical costs, the gel breakers, pH buffers, crosslinkers, demulsifiers, all just went away overnight. Similar kind of evolution with conductivity and the need for conductivity, the realization that sand can do things that we never thought it could do. You would never pump sand in the closure stresses. We pump it in every day today, and we do it successfully. And the next evolution of proppants, frankly, probably hasn't even been attempted yet, because there's room there for new technology that the industry hasn't yet tested or adopted. On the denominator side of the equation, we've gone down the path of cost reduction. We've gone down the path of improving BOEs produced simply by magnifying those cost savings into a greater scalability. So by dropping all those costs, what it's done is it's paid us to pump more of it. And so we've affected the BOE produced, more sand, more fluid, more rate, more hydraulic horsepower. But fundamentally, we've kind of come to the end. Pumping 50 million pound fracs is probably a little over the top already. So how do we drive cost out of a system where we're pumping plain water, in some cases not even putting the friction reducer in it? What do we replace massive volumes with something that's cheaper than water, untreated water? Of course, water costs aren't the cost of the water. It's the heating, it's the hauling, it's the disposing. It's all the ancillary stuff that comes with water. And of course, there's a significant environmental and social license cost that comes with using water. Because as far as the public is concerned, the industry has no right to take water out of the water cycle and put it in the ground and never get it back. And so that cost might become the bigger of those costs in the longer term, and certainly will become the bigger cost. But for now, it's all about the dollars. So when we look at what's available on site and doesn't need disposal, doesn't need hauling, doesn't need heating, et cetera, we got the air we're breathing, we got the soil we're standing on, and on these multi-well pads, we've changed all the rules, and we've got natural gas, and plenty of it. And so there's technology available, well, pseudo-available. Technology has been developed to allow us to use compressed, cooled natural gas as a frac fluid. Essentially take 80 to 90 to even 95% of the water out of the equation. The water is only used basically to carry the sand through the blender and then deposit it into a frac fluid largely made of compressed natural gas. The beauty of this is it eliminates a lot of the other things that come with what we do today in the world of fracturing. If you did this with CO2 or nitrogen, of course, you're going to flare for an extended period while you clean the well up. With this, you're going down the sales line. We, of course, eliminate all the water issues, and the beauty is, when you do the math, this could save a tremendous amount of money on a per well basis. A company by the name of Expansion Energy is developed what they call this verge process. I included these next two slides simply so that people would have a reference. If you want to go look it up, you can pursue it. But they've done some very detailed cost studies on a play-by-play basis, looking at the cost of hauling the water, doing all the things we do. They've compared CO2 fracs, CO2 foam fracs, N2 foam fracs, and slick water fracs against this process. And I mean, they come up with savings using this methodology of upwards of $2 million a well. That's a lot of cash. And certainly as we're in well manufacturing mode and doing 20, 30, up to 40 wells on a pad site, the ability to implement this kind of a solution becomes a potential game changer. The methodology uses this metacritical phase that they define, so you can handle the methane as a pseudo-liquid. It takes a lot less horsepower, obviously, while pumping the frac because it becomes more incompressible. It's not truly incompressible, but makes it handle more like a conventional foam frac fluid. Second way we can deal with this, we can change our methods. And today we've learned, because of the systems that were available to us, that we start at the toe of a well and we start putting frac stages in from the toe backwards. And the press and the media likes to use the word blasting the formation. You know, we've built this public image up that we're, you know, setting off little bombs down the hole and really doing this explosive function when we fracture a rock. In truth, we're performing work on the formation. I mean, we expend all of this horsepower over hours, many hours in a multi-stage horizontal well. It's kind of like having a slow motion bomb. I mean, a bomb's a dangerous device, but if it took 45 minutes for the pressure wave to get to you, it wouldn't be a terribly dangerous thing. And that's what we're doing downhole. We're performing work, so a force through a distance. And by changing the sequence that we put these fracs in place, we can change the amount of resistance that the formation gives us and allows us to put more work into it. Because if I can apply more force, get more resistance against that force, I can apply more work and potentially change the way the rock breaks. So that would allow us to change our stimulated reservoir volume via generating our own frac complexity, as David alluded to earlier. And it has a nice side benefit that in formations like the Montney, for example, where we've got unlimited pay height, more pay height than we can complete with a single frac, we can affect that hydraulic fracture height and potentially eliminate entire layers of well bores where, you know, operators are going in and planning 2 and 3 layers of wells in these really thick formations. Today, that very methodology is being used in what we call zipper fracs or modified zipper fracs. So, you know, we're either using the disturbance of an offsetting wellbore frac to blunt the frac here, allowing us to build net pressure and affect the rock fabric, if you will, or interlacing them and letting the stress field be multiplied between these fracs. There's 2 things that suffer in this, is that you've got simultaneous operations. Number one, you run the risk of well bashing and having these fracs take away a well from you, essentially, by having that happen. And it becomes a complex process. That deformation of the rock that's caused by the fracture is a vehicle for us that we can use to our advantage if we know how to handle it. There's been a lot of papers written about how to avoid stress shadows. You know, because when you're doing things sequentially, the stress keeps adding up. And so if we look at these 3 fracs here, the first one being in blue, then the gold, then the red, and the size of this shadow, the frac is in the middle here, this gives an indication of the stress increase associated with that frac. So over here on the right, after frac 3, I've got the sum of frac number 1, 2, and 3 all working together to boost the stress next to those in that formation of interest. And so most of the theory out there basically says, well, we want to space these far enough apart that these frac shadows never boost the stress that I've induced in my pay area high enough to break me through this barrier, because that would be wasted in a conventional thin pay kind of a completion. With using that to our advantage, if we're able to place fracs out of sequence, so we place the first frac on the left, second frac on the right, and then propagate a frac through the middle, we can generate this area, a large volume of rock, where the stress has been artificially enhanced, artificially boosted. And so if there's fabric in that rock, if there's old fissures, if there's old surfaces that can be caused to shear, caused to slip, to give a secondary permeability that we wouldn't otherwise be able to enjoy, we can induce our own complexity. One of the nice sidelines of that is, you know, when the engineers in the reservoir group do their tornado diagrams on what's the most important things in comparing wellbore performance, without doubt, one of the top 2 is always K and always H. KH kind of drives the number 1 thing that we deal with. So if in thick formation pays, we can change that H substantially by taking this kind of an approach. This is just gopher frac models of 2 fracs. This is the original bookend frac. So placed by itself with no stress shadows around it, this is what we would get. The wellbore is shown here. It grows to this height with these dimensions. And this was just off of an actual log suite in the Montney. Take the same pumping schedule, place the well in the same spot, but bookend it with these 2 fracs. And I believe this was about 100 feet away. This frac dimension, as you can see, is significantly affected by the presence of these other fracs. But our industry has never been capable of doing fracs out of sequence in any sort of a practical manner. But with the advent of these closable frac sleeves today, doing a frac 1-3-2 instead of 1-2-3 is frankly no operational hurdle whatsoever. It's basically moving an extra 100 or 200 feet up the well, that's it. So we would start at 1, then jump to 3, and then when we put number 2 in between, potentially generate this complexity that we can't get any other way, because we've got no way to make the formation resist us aside from conventional zipper fracs or modified zipper fracs. But we can do this now with a single wellbore and have potential significant impact on the productivity of the well. In all of the literature search that I was able to do, I could only find 1 example of this actually being executed anywhere in the world. There's lots of SPE papers written about the potential of this. There's a number of numerical simulators that have been run to exercise what are the what-if potentials of it. But there's only 1 application of it that I could find. That was a 2014 Lukoil annual report where they had done 8 wells. This is snapshots right out of their report. They did 8 horizontal wells in 2013 and 2014 using this out of sequence methodology, and got somewhere between 200 and 400% productivity out of those modified wells. So I was told off the record that they had used a methodology that kind of predated the multi-cycle frac sleeve. They would have to go in and use 1 tool to open the sleeve, then come out of the hole with coil tubing, put a different tool on to close the sleeve, and repeat that process through the well. So it was extremely painful, I have no doubt about it. Today that's not the case. We simply shift the tool, open, frac it, and then close it. Final slide before we turn it over to questions. And this, keeping with the movie theme, is the coming soon technology, because it frankly doesn't exist yet. But it should push us again over that edge, and that is a self-shifting frac sleeve, something that we communicate with. It'll do three things. It'll open itself, it'll close itself, and then it'll open itself again. And so what that will allow us to do is, A, take the cost of coiled tubing off the table for the initial completion, but it opens up the wellbore to higher pump rates if those are still desirable. I honestly believe that things in that out-of-sequence fracturing might make high pump rates completely obsolete, because today we do a lot of that to try to generate that complexity and try to generate frac height, and it might not be necessary at all anymore. We can all obviously continue to facilitate things like frac sequencing simply by programming the sleeves to open in different orders, and keep the full drift ID while maintaining future needs to open or close a sleeve with coiled tubing and facilitating therefore refracs. And those are planned for release in the coming year. So hopefully to a theater near you soon. And with that, I'll turn the floor over to questions and concerns. My hope is that the edge we're on, the edge of tomorrow, looks a little more like this than in the original slide. And I think with some of the technologies that we're using to build on each other, we can make that step happen pretty transitionally easy. Thank you.
Do you have any questions for David or Eric? Can you please come to this mic here? We're going to speak on the live streaming portion of the speech. And speak up as I find out. Or if you don't mind, give us a mic up. So any questions, please come up and listen to David.
Randy Freeborn with Energy Navigator. I always have questions. David, in your slide you showed us a lot of statistics at the beginning, and what I'm seeing is what to me is a disturbing trend of what I call one-dimensional analysis. So we know there's 5 or 6 things impacting stuff, but the last Montney workshop in the US and here today, seeing a lot of performance information against one parameter. For instance, you looked at proppant loading without looking at what other things might have been influencing the performance at the same time. Can you comment on that and ways that we can get around a one-dimensional analysis using public data?
Yeah, no, that's a very good point. That's if I go back to I think the answer to your question, Randy, lies in this sort of in this sort of work. But you're absolutely right. As an industry, and I talked about this quite a bit in my first talk. As an industry, we try to find one-dimensional, two-dimensional trends, and it's often an oversimplification of what's going on. So what I tried to do today was more just to see which way are the averages moving. I wasn't trying to draw any specific conclusions about proppant. 2 things you need to do. One is you need to really dive into a smaller individual subplay if you really want to understand. And we've done, our team has done that work in a much deeper dive. Problem is, you need operator data to do a good job of that. So to answer your question, how do we do this with public data? I think the answer is in something like this, where you build a data model, a data-driven model that recognizes that it's a multivariate problem from step 1, and uses some of these tools, these machine learning tools, to help solve these problems. It's not a silver bullet. You have to have an experienced petroleum engineer doing this. It's not just data science and we're going to get the answer at the end. But I think that's where you need to go. You need to use some of these statistical and data mining tools that recognize that these are multivariate problems and solve them that way.
Thanks.
Robert Hawks from Trican. This one's for you, Eric. So you taught me years ago rate, pressure, viscosity, what's creating complexity. So I really enjoyed your talk. My question to you is Eric and Robert Coe going to arrive with a big gas compressor? And are we going to be pumping for a week or 2 weeks into these wells? Is that how you could even envision this new idea? I think you might be onto something.
Potentially, I think that's, I mean, today the drive for rate is really all about trying to change the rock on one hand and to reduce cost time of the frac crew on location, if you will. If you scale the frac crew down to where rate doesn't matter, time on location becomes a lot less important variable as well. And if you start to not use water and have all of that go with it, it becomes a very viable thing. Now, I'm not saying that we're going to pump all fracs at 2.5 cubes a minute, but I'm certain we won't have to pump them at 10 anymore.
So any more questions for Eric or David? If none, then I'd like to bring the session to an end and thank our speakers this morning for a really interesting talk. And I'd like to thank you from the SPE Calgary section with a little gift that I will bring over there for both of you. And thank you again for sponsoring the series. And with that, I'd like to bring the session to a close and thank everyone this morning for attending.